back. So here's the lecture 1 that is focused on foundation concepts of software engineering. In this lecture we will understand how existing software systems are studied, improved and transformed, and how to work with and modernize the real world software systems. For clarity, we have divided this lecture into 5 parts to make it easier to understand. Here's the agenda. Let's start with the first one, that is defining software engineering. Software engineering is a software development process focused on improving the maintainability of the existing system. Instead of building software from the scratch, we work on an already developed system and enhance its structure, readability and long-term usability. In simple terms, it is the examination and modification of a software system to transform it into a better and you can say more organized form while preserving its functionality. This process is not a single activity but a combination of several you can say sub-processes. It includes reverse engineering to understand the existing system, restructuring to improve its internal design, redocumentation to update or create clear documentation, forward engineering to rebuild or enhance the system, and retargeting to adapt it to new environments or platforms. Together, these steps help in transforming complex or outdated software into a cleaner, more maintainable and modern system. Software reengineering is motivated by several practical needs in real-world software systems. First is cost saving. Due to reduced government and industry budgets, organizations often cannot afford to build completely new systems from scratch. Instead, they try to adapt an existing system to support new requirements. For example, a banking system may be updated to include mobile banking features rather than developing a new system entirely, significantly reducing the development cost and time. Another major reason is the reducing maintenance cost. In many systems, changes are directly made in the code without updating the design documentation. So over the time, this creates a gap between the actual system and its documentation. As a result, maintainers struggle to understand how the system works. For instance, a telecom billing system with outdated documentation may take weeks to modify a software for a new tariff policy, for example. Reengineering helps to restructure both code and documentation, making the system easier to understand and maintain. A key motivation is also a design recovery. In many legacy systems, important design information is lost over time, especially when original developers are no longer available. This makes organizations dependent on few individuals who understand the system. Through reverse engineering, we can recover this hidden insight or design knowledge and document it properly and reduce this dependency. For example, recovering the architecture of an old hospital management system helps new developers quickly understand and maintain it. Reengineering also helps in identifying trouble spots in the system. These are the parts of the code where errors frequently occur or performance is poor. By analyzing and restructuring such areas, we can improve the system reliability and performance. For example, a slow reporting module in an enterprise application can be optimized after identifying bottlenecks during reverse engineering. Another important motivation is migrating systems to newer environments. Many old systems are built for outdated platforms but still contain valuable functionality. Reengineering allows us to move these systems to modern platforms without losing core features. For instance, moving a desktop-based payroll system to a cloud-based environment ensures a better accessibility and scalability. Finally, software reuse is a major advantage. Existing systems often contain useful and tested components that can be reused in new applications. Instead of writing everything again, these components can be extracted and reused efficiently, saving time and effort. Together, these motivations show why software engineering is essential for managing and improving complex and real-world systems. Reengineering refers to a one-time or well-defined cycle where an existing software system is taken, analyzed, and transformed into a new improved version. The focus is on restructuring or rebuilding system to achieve better maintainability, design quality, or platform compatibility at a specific point in time. In contrast, software evolution is a continuous and ongoing process. Software systems keep changing throughout their lifetime as new requirements emerge, bugs are fixed, and features are added. So this process doesn't have a fixed end. It can continue as long as the system is in use. Evolution represents a never-ending journey of change and adaptation in software system. Software engineering can be understood as a combination of reverse engineering and forward engineering. First, reverse engineering is used to analyze and understand the existing system, its structure, its design and functionality. Then necessary improvements or modifications are identified, represented here by delta, meaning change or enhancement. Finally, forward engineering is applied to rebuild or restructure the system into a better and more maintainable form while preserving its core functionality. So in simple terms, re-engineering means understanding the old system, improving it, and then constructing an improved version of it. Reverse engineering is the process of analyzing an existing software system to understand how it works internally. In reverse engineering, the main input is the source code of the system. Developers study the code, modules, data flow, and relationship between the components in order to recover the high-level information such as the system architecture and system design. The output of this process is not a new software, but a better understanding of the system itself. For example, if an old banking application has a poor or missing documentation, then reverse engineers can help the developers to identify how different modules such as account management, transactions, and authentication interact with each other. An important point to remember is that reverse engineering focuses only on examination and understanding. It doesn't involve modifying or changing the software. The system remains exactly the same during this process. Forward engineering is the traditional software development process where we move from high-level concepts and design towards the actual implementation of the system. In this process, the developers begin with the requirements, architecture, and design models, and then convert them into source code, databases, interfaces, and working software components. Unlike reverse engineering, which focuses on understanding an existing system, forward engineering focuses on building or reconstructing the system. For example, after analyzing and redesigning a legacy banking system, developers may use forward engineering to implement the improved architecture into a modern web-based application. The final output of forward engineering is the functional software system that meets the required design and business objectives. So forward engineering is essentially the process of transforming the ideas, the design, and specifications into a real working software product. Delta refers to the changes or alterations made to the original software during re-engineering. These modifications are the improvements identified after understanding the system through reverse engineering and before rebuilding it through forward engineering. There are two major dimensions of these alterations. First is the changes in functionality, which means modifying the business rules or system behavior. For example, an e-commerce system may introduce a new payment policy or discount rule or maybe a user feature based on updated business requirements. Second dimension is the changes in implementation technique. This involves improving the technical side of the system, such as migrating maybe from a procedural programming language to a object-oriented language or moving from a desktop application to a cloud-based architecture. For instance, an old payroll system written in maybe COBOL might be redesigned and implemented using Java or modern web technologies while preserving its core functionality. So Delta represents the transformation phase where the system is enhanced, modernized, and prepared for a better future implementation. Legacy systems are older software systems that continue to play an essential role in supporting business operations and organization processes. Even though the systems may use outdated technologies or architectures, they are still extremely important because businesses depend on them for daily activities. For example, banks, hospitals, telecom companies, and government organizations often rely on legacy systems that may have been running for many years. However, over the time, these systems become difficult to maintain, difficult to understand, and difficult to modify due to the outdated code, the missing documentation, and increasing complexity. Software engineering focuses on re-implementing or improving these legacy systems so they become more maintainable, reliable, and adaptable to modern requirements. For instance, an old airline reservation system may still function correctly, but re-engineering can modernize its structure and technology to make future updates easier and safer without changing the core functionality. So the main goal of software engineering is not to discard the legacy systems but to improve and modernize them while preserving the valuable business logic they already contain. Software change is inevitable because software systems operate in continuously changing environments. As the users use the system, new requirements naturally emerge. For example, an online shopping platform may later require digital wallets or recommendation systems, or multilingual support may be based on the user needs. Business environments also change continuously. New regulations, market trends, or organization policies may require updates in the software. For instance, banking systems often need modifications to comply with changing financial regulations. Another important reason for change is error correction. No software system is completely free of bugs. So issues discovered after deployment must be repaired to ensure the correct functionality. Technical evolution also drives software change. New computers, devices, operating systems, or cloud platforms may require existing systems to be adapted for compatibility. Finally, organizations often need better performance, security, and reliability. For example, a growing social media platform may need optimization to support millions of users efficiently. All these factors make software evolution a continuous and unavoidable process. Software maintenance refers to modifying a software system after it has been deployed or put into use. These modifications may include fixing bugs, improving the performance, adapting the system to new requirements, adding limited functionality. So maintenance typically doesn't involve major architectural redesign. Instead, developers work by modifying existing components and adding new ones occasionally. For example, adding a new report feature to an existing payroll system, or maybe fixing calculation errors in a billing application, are common maintenance activities. Maintenance ensures that a software continues functioning effectively throughout its operational life. Organizations invest enormous amount of time, money, and effort into their software systems, making them critical business assets. For example, air reservation systems, hospital databases, and banking applications are deeply integrated into daily operations. So replacing them completely would be extremely expensive and risky. To preserve the value of these systems, organizations continuously update and improve them instead of discarding them. As a result, a large portion of the software budget in major companies is spent on maintaining and evolving existing systems rather than developing entirely new ones. So this highlights why software evolution and re-engineering are so important in modern software engineering. Software systems exist with dynamic environments, and those environments continue changing even while the software is being developed. As a result, by the time the system is delivered, some original requirements may already have changed. For example, customers' expectation, the market conditions, or maybe business policies may evolve before the deployment is complete. So software systems are also tightly connected to their environments. When a new system is introduced into an organization, it often changes the workflows and the processes, which then creates a new requirements for the software itself. This means software cannot remain static. To stay useful and relevant, softwares must be continuously maintained and adapted to changing conditions. All of the support activities performed after the software delivery are generally categorized as maintenance. However, activities specifically aimed at adapting software to changing requirements fall under software evolution. So software evolution goes beyond simple fixing problems. It focuses on continuously improving and adapting the system over the time. Software evolution is usually described as a process of conducting continuous software re-engineering, you can say. So this means software systems constantly undergo analysis, improvement, restructuring, and adaptation throughout their life cycle to remain useful and maintainable. Let's test our understanding with a quick interactive quiz based on a real-world software modernization scenario. Before attempting the quiz, remember the key differences. The backward engineering focuses on understanding and recovering the information from the existing system, while forward engineering focuses on designing and building new functionality. The team studies old source files to understand how discount and tax are calculated. So is this forward engineering or backward engineering? So the correct answer is backward engineering. because the team is analyzing an existing system and they are recovering the hidden business value and no new feature is being built. Next, consider this scenario. The team interviews experienced cashiers to uncover undocumented practices like festival discount and free reward items for loyal customers. So is this a forward engineering or backward engineering? This is backward engineering because the team is extracting hidden information from the existing system environment, and the discount practices and the reward rules already existing in daily operations, but they were never formally documented inside the software. By interviewing the long-term employees, the team is recovering the old business knowledge so it can be preserved in the modernized system. So the focus here is on understanding and recovering the existing behavior, not building new functionality. The team performs test purchases and returns in the old system to observe how billing, taxes, and inventory updates work internally. This activity represents backward engineering because the team is studying the behavior of the existing system to understand its hidden workflow and logic. By testing purchases, discounts, and returns, they are discovering how billing and inventory processes actually operate behind the scenes. Their goal is analysis and understanding, which are the key characteristics of the backward engineering. The team separates billing, inventory, and reporting into independent modules to improve the maintainability and system organization. So this is forward engineering because the team is redesigning the system architecture into a cleaner and more modular structure. And instead of simply analyzing the old system, they are actively creating an improved design that will make the future maintenance and development easier. So this activity involves constructing a better system organization, which is a part of forward engineering. Company plans a new mobile-friendly application that allows the customer to order groceries online for the first time. So this feature never existed in the original system. Team is planning and developing a completely new capability for customers. So think carefully about which engineering approach this fits. This activity is again forward engineering because the development team is building a completely new feature from the scratch. Online ordering didn't exist in the old system, so the focus here is on design, development, and implementation of new functionality. And forward engineering always involves moving towards a future system with new capabilities and improvements. The development team creates a loyalty rewards feature that gives customers points for repeat purchases. This represents forward engineering because loyalty point system is a newly designed feature that didn't previously exist, and the system is creating new business functionality and integrating it into a modernized system. Since the focus is on development and implementation of improvements, future improvements, so this is clear example of forward engineering.